To find the molarity in this scenario, the first thing I need to do is look up what the molar mass is for each of my elements. So what I have behind my whiteboard here, this is ptable.com. And it is an interactive periodic table that has an awful lot of properties on it that you are welcome to use if you find that necessary. So the reason I had to go there for the molar mass was because what I'm given is a mass of a compound. And this compound may be in a form that you might not be used to. So this is Na2SO4. This is sodium sulfate. And then there's a dot 10 H2O. And what this means is that it's hydrated. So for every one sodium sulfate, there are 10 water molecules. Now we need to take those 10 water molecules into account. So when we go to calculate our formula mass of this compound, those 10 water molecules are going to be necessary. So we need to count the number of atoms of each of these elements that we have. So I have 2 sodiums, so I'm going to put a times 2 here. I have 1 sulfur. And oxygen, I have 4 oxygens here, but I have 10 oxygens here because what I do is I multiply the coefficient by the subscript. So I have a total of 14 to multiply here. And for hydrogen, I have 20 because again, I take that coefficient and multiply by that subscript. So I'm going to find the molar mass of this hydrated sodium sulfate. So in my calculator, I have 22.99 times 2. And I'm going to add that to 32.06. Add that to 0.999, which is what's given in my ptable.com. Your periodic table may round to the nearest like hundredth place, and you may get 16.00. That's okay. So I have my 15.999 times 14. Then I'm going to add that to 1.01 times 20. So the molar mass I get for this hydrated compound is 322.226 grams per mole. Now the point is we are looking for molarity. Now molarity is moles of the solute over liters of solution. 99% of the time when you see grams in a general chemistry course, you're going to need to convert it into moles. So what we're given is kilograms. Well, a kilogram, 1 kilogram is 1,000 grams. So I'm going to set up this dimensional analysis. Dimensional analysis is a great technique when working a lot of these problems because what we're going to do is use the unit as if it is an algebraic factor and we're going to cancel it out. So just what I have here, kilograms is going to cancel with kilograms, and when I multiply these two numbers together, then I'm going to be left with grams. Theoretically, if your units work out, your problem is set up correctly. So the way that I read this molar mass is this is 322.226 grams per 1 mole. So the 1 stays with mole, and I'm actually going to label it Na2SO4 hydrate. And then the 322.226 grams of stuff goes on the bottom. That way the gram cancels with grams, and I'm left with moles. So to complete this calculation, I take 10.5, multiply it by 1,000. Then I'm going to divide that by 322.226. So you don't have to remember a formula, you just have to make sure that the units all cancel out correctly. So I get 32.5, and I'm going to give you too many significant digits here. 5, 8, 6. Nah. No, let's not do too many significant digits. There are 3 sig figs here. Let's give it 3 sig figs. So this is going to round to a 6. 32.6, and that is moles of my compound, my sodium sulfate decahydrate. Okay? But the point is we need to find molarity. So I also need liters, and I'm given those liters here. So capital M molarity is going to be equal to moles, so 32.6 mol moles, divided by 18.60 liters. So I take 32.6 divided by 18.6, And now I'm going to say that this should be 3 significant digits, 1.75 capital M molar is going to be my answer because I had 3 significant digits in this measured quantity. This measured quantity has 4 significant digits, but my answer is going to be bound by the 3 sig figs here. Hope that helps.